So in this video, we're going to be looking at the classification of our alcohols, followed by the different oxidation reactions they can take part in to form different products. Now starting off, we know that alcohols can be classed as either being primary, secondary or tertiary, just like our carbocations. We already looked at this in our alkenes topic, where we said we can end up with different alkyl groups like methyl, ethyl. Of course, it's just going to be like a branch almost. Where we look at, let's say, a primary alcohol, we can see the alcohol is here, the carbon atom it's attached to is this one over here. How many alkyl groups, how many carbon atoms is that going to be attached to? If it's 1, we say it's going to be primary. If it's going to be, in this case, 2, we can say it's going to be secondary, where you can see I've got 2 alkyl groups over here. And then if you've got 3 alkyl groups, 3 carbon atoms attached to the carbon atom that's attached to the alcohol, we know it's going to be tertiary. So now that we know about the different types of alcohols we can get, we need to be aware of the different types of reactions, the oxidation reactions we can get with each type of alcohol. Now, different classifications of alcohols, they can actually be oxidized to form different products, where we can end up with a carboxylic acid, a ketone, or even an aldehyde as well. But the thing that determines the product that we actually make is going to be, first of all, what type of alcohol we've got, and then secondly, the condition that we've actually got, because different conditions produce different products. Now, if you look at what oxidation means, it's basically when our alcohols, they react with the oxidizing agent. That's going to be the stuff that helps our alcohol be oxidized, in itself being reduced, and we represent that normally in our balanced equations using some square brackets and an O. If you were to look at a reducing agent, you would put a H in square brackets instead, but of course that's going to be for a later topic when we look at a reduction of carbonyl compounds. Now, of course, we can form aldehydes, carboxylic acids and ketones from this as well. Now, we're going to start off with this first alcohol over here. We've got a primary alcohol, that's the classification I'm giving it. Why? Because the carbon atom that the alcohol is attached to, we know it's got, of course, 1 alkyl group, so in that case it's going to be primary. Now, the first reaction when it comes to oxidizing our alcohols is going to be when we form an aldehyde from a primary alcohol. The key condition that we need every single time is going to be potassium dichromate. That's going to be our oxidizing agent, where it's going to be oxygen in square brackets, and then of course an acid catalyst, which we know is going to be H2SO4. Of course, you can end up with different catalysts and different oxidizing agents, but these are the ones that we need to know from this spec. The key condition to produce an aldehyde is going to be distillation, and that actually produces, of course, a carbon oxygen double bond there. We've got rid of the OH group and we end up with this aldehyde over here. The number of carbon atoms is still going to be 3, it's still going to be the same. I've got propan-1-al over here, and over here I've got propanal. The aldehyde has been formed. The functional group in this case has been changed. Now, the key condition for this reaction to happen is going to be that we need distillation, because distillation will stop it from turning into a carboxylic acid. And that's going to be our next reaction. This aldehyde, if we were to react it with another equivalent, another lot of oxidizing agent, what we can actually end up forming is under the conditions of reflux this time, we can actually form a carboxylic acid over here. And that carboxylic acid, again, you can see that carbon oxygen double bond, that functional group from an aldehyde has changed into a carboxylic acid one, which you can see over here. I've formed propanoic acid in this case. Now, let's say if I wanted to form a carboxylic acid from a primary alcohol, I didn't want to do it in 2 steps where I went with distillation and then reflux. I could just reflux it from the start, and as soon as the aldehyde is actually formed, we end up actually producing the carboxylic acid. It will continue to react straight away, and we end up producing a carboxylic acid straight from a primary alcohol. So of course we do end up with this 2-step process. It goes from a primary alcohol to an aldehyde to a carboxylic acid, but of course we're doing it in one reaction vessel. So there's a reaction for our primary alcohols. What about our secondary alcohols? Well, over here I've got propan-2-al. The carbon atom that's bonded to the alcohol is there. It's got 2 alkyl groups attached to it, so we know it's going to be a secondary alcohol. Now, what we can actually do over here is we can oxidize this using the same conditions again. We don't really need distillation in this case, although it would have the same effect. Reflux or distillation doesn't really matter. You can actually form a carbon oxygen double bond, replace that with the OH. You can actually form a ketone in this case using similar conditions of primary alcohols. You can see you've gone from, of course, propan-2-al, and you formed here propan, and then it's going to be one. You can call it propan-2-1 as well, but we're just going to call it propanone. Now again, remember, you can actually have distillation or reflux, doesn't matter in this case. For the secondary alcohol, it will still actually produce the ketone, and you still have the oxidizing agent and the acid catalyst. It's going to be, of course, above our arrow over here. Now, if you were to look at, let's say, preparation techniques and look at distillation and reflux in a bit more detail, reflux, we use it to react volatile substances together to prevent substances from escaping. If I were to look at a reaction again, where I'm taking, of course, a primary alcohol. In this case, I'm going to go with something easier. I'm going to go with ethanol in this case. If I were to take ethanol and react that with my oxidizing agent, I would put that in, of course, my round bottom flask that you can see over here. I'd have attached to it a condenser where the water is going against gravity. It's going in on one side, going out on another. Of course, it's going to be a jacket that cools the actual gases down. When we heat our oxidizing agent, our alcohol, and then don't forget your H2SO4 as well, what happens is of course this reaction will take place in our round bottom flask, and when our aldehyde is going to be produced, we end up with, of course, in this case I end up with ethanol. Ethanol is going to evaporate away, and the thing is, if we were to do this in a beaker, it would just evaporate away and it wouldn't react further to produce a carboxylic acid. So to actually turn that into a carboxylic acid, because so far we've turned it into an aldehyde, we would actually use a condenser, which would cause the actual gas to condense, and it would condense down, trickle back into the solution so that it can actually continue reacting with our oxidizing agent. And that's how we can force the reaction to go through further and we form a carboxylic acid. Now, a point to mention is that when we deal with organic synthesis, reflux is always used when we're dealing with volatile organic compounds, because we don't want our product or our reactants to evaporate away. We want them to continue reacting, especially if they've got very different melting and boiling points. If we were to look at distillation, distillation is only used in one case, and that's when we want to go from, of course, our alcohol. Let's say in this case we're dealing with ethanol again, and we want to form, in this case, an aldehyde. Now, how is the distillation apparatus going to be different compared to a reflux? Well, if you look at distillation, we've still got a round bottom flask, we've still got heat supplied in the form of a water bath. We use things like graphite baths or heating mantles because they seem to be a lot safer compared to, of course, naked flames. A lot of our organic compounds, they're going to be flammable. Now, when this reaction happens, we know, of course, just like before, our aldehyde is produced. It's going to have a lower melting and boiling point because, of course, it no longer has hydrogen bonding compared to our alcohol. We end up with, of course, that evaporating. It's going to evaporate away. Now, unlike our reflux apparatus, when our aldehyde is produced, of course, it's going to go into the condenser. We've got water going in at the bottom, water going out at the top. We know, of course, we do this. It goes against gravity. We're preventing a thermal equilibrium from being established. We're continuously replenishing this with cold water so that, of course, our aldehyde will cool down. It will cool down, it will condense, and then, of course, it will go through our delivery tube into our collection flask, and we've got pure aldehyde being produced there. Now, of course, we've removed our aldehyde before it reacts any further, so we don't actually end up with the second reaction taking place to form our carboxylic acid. And so this is what makes distillation different compared to reflux. Now, one other thing to be aware of is when we look at reflux and distillation, we're using them here as preparation techniques, but they can actually be used, distillation anyway, it can be used to purify an organic liquid, and that's something that we look at in our synthesis topic. So yeah, moving on then, looking at our reactions in a bit more detail, because of course we need to be able to produce balanced equations for these as well, predict some products and predict some reactions too. If we were to look at our primary alcohols, they can actually be oxidized to form our aldehydes, which we already know, and the apparatus that we need is distillation. If we were to look at the reaction conditions, we need, of course, potassium dichromate, which is K2Cr2O7. You might see in the exam as well as Cr2O7 and then 2- because that's a key ion that we're after. If you were to look at our acid catalyst, in this case that's going to be H2SO4, sulfuric acid, and of course our apparatus that we need for this reaction to produce an aldehyde is going to be distillation. Now, the examiner might actually refer to this as being partial oxidation as well, because you're partially oxidizing the alcohol to form an aldehyde. If it was complete oxidation, you're forming a carboxylic acid. I've got propan 1 all over here. I've got my oxidizing agent, of course that's going to be my reactants. Above the arrow, I've got my oxidizing agent, H2SO4 and distillation, and you can see here I've formed propanol and 1 lot of water. Now, that's the oxidation of an alcohol using, of course, distillation apparatus to form an aldehyde. What about if instead we were to oxidize this alcohol again, the same alcohol, but this time we would produce a carboxylic acid if we use reflux apparatus. Again, the oxidizing agent, the acid catalyst is the same. The only difference is we've got reflux here instead, and just by changing that key condition, we can actually end up producing propanoic acid from propan 1. Again, we call this complete oxidation rather than partial. We end up using 2 lots of oxidizing agents, but one mistake a lot of students make is that they forget that we only produce 1 lot of water. We do not produce 2 lots of water. You can see, of course, the reaction equation is very similar, but just remember you're going from a primary alcohol, 2 lots of oxidizing agent, reflux is the condition, and here you're producing a carboxylic acid, propanoic acid, and one lot of water. Now if you were to move on, we could look at oxidizing aldehydes. This equation is quite a weird one because aldehydes, we already know they can be oxidized to produce carboxylic acids again, but of course this time we're using reflux apparatus. We have to use reflux apparatus because our aldehyde will just evaporate away if you use distillation. If we were to look at the reaction conditions, again it's the same as producing a carboxylic acid from a primary alcohol, but here we react it with one lot of oxidizing agent, but you don't actually produce any water. There is no water present in this reaction. If you were to look at secondary alcohols, these could be oxidized to produce ketones this time, and we're using reflux apparatus. You can use distillation as well, but of course we use reflux because we want a high yield of our product. Reaction conditions, again same thing, oxidizing agents there, sulfuric acids there, reflux, but this time we're forming the carbon oxygen double bond. We're forming it on the 2 position over here. So again, I'm taking propan-2-ol, one lot of oxidizing agent, I'm making propanone, and then of course one lot of water as well. Now one alcohol that we've not actually mentioned is going to be our tertiary alcohols, and tertiary alcohols, they can actually react in oxidation reactions. The reason why is, let's say if I were to look at 2-methyl propan-2-ol, if I were to oxidize that, theoretically what I would end up producing is of course 2-methyl propan-2-ol, which of course is not going to exist. The carbon atom has too many bonds. Now this bit of theory is going to be quite important when it comes to testing for the difference between a primary or a secondary alcohol versus a tertiary alcohol. What we can do is we can add a few drops of potassium dichromate 6 solution. Remember the 6, that's the oxidation state of chromium, and then of course we would add a few drops of concentrated sulfuric acid catalyst. Now if I've got a primary or secondary alcohol, I would end up with the color change going from orange to green, and what that shows me is of course my chromium is going to be reduced. I end up with an orange over here for the potassium dichromate 6, and then when it's reduced you end up with of course a green solution. Of course we know our alcohol is oxidized, our chromium is going to be reduced. That's why we call the potassium dichromate the solution. It's going to be of course our oxidizing agent because it helps our alcohol be oxidized. Now of course if we were to look at our tertiary alcohols, because we can't actually oxidize them, the addition of potassium dichromate 6 and concentrated sulfuric acid would lead to no reaction, and so we see no visible change, and our solution is going to remain orange itself. So of course we don't actually see this reaction happen. Now moving on, I've got a task for you to do. I want you to give the equations for the following using of course skeletal formula. Pause the video, have a go, resume once you're ready to go over the answers. So you're looking at the first question. We're told first of all we've got oxidation as a reaction, and it's going to be complete oxidation over here as well. We've got an alcohol which we need to decide is going to be primary, secondary or tertiary, and we've got reflux apparatus here as well. Now if I were to look at it, I've got butan-1-ol. Always draw it out first of all to check the actual reaction. We've got reflux taking place. It's going to be a primary alcohol. We know we would end up with a carboxylic acid. So I end up with of course butan-1-ol, which looks like this. That's going to go ahead and it's going to react with some oxidizing agent. We'll balance it at the end. We end up producing of course butanoic acid, which is going to look like this, and then of course we also produce water as well. Now if we were to actually balance this equation, we would end up with 2 lots of oxidizing agent, remember, and then 1 lot of water being produced, and there's the first one done there. Looking at the next one, we've got the partial oxidation of 2-methyl butan-1-ol using distillation apparatus. Well, if we were to look at this, partial means that we're producing an aldehyde. We're not going all the way to produce a carboxylic acid. We're using distillation apparatus here, some more hints that we're producing an aldehyde. Now 2-methyl butan-1-ol, what type of alcohol is it? Well, there's 2-methyl butane. There's 2-methyl butan-1-ol. We look at the carbon atom here, it's only attached to one alkyl group, so we know it's going to be primary again. So in that case, I end up with, of course, my carbon atoms. I'm going to end up with 1, 2, 3, 4 methyl there, and then the alcohol is going to be over here. I end up reacting it with oxidizing agent again. We'll balance it at the end. We end up producing, of course, not a carboxylic acid in this case, but instead we produce a aldehyde. And so I end up with something that looks like this, and I also produce water as well. And there you can see, of course, my equation actually balances. We need 1 lot of oxidizing agent. We produce 1 lot of water. Looking at the last one, I've got the oxidation of cyclohexanol, and we're using reflux apparatus over here. Well, first of all, cyclohexanol, I'm going to draw it out like this. So my OH is over here. I've got my carbon atom of interest. I've got 2 alkyl groups. I know it's a secondary alcohol. That means I'm going to produce a ketone. So in that case, I'm going to end up with, of course, my cyclohexanol over here. There's my molecule. I'm going to react it with oxidizing agent, And then of course I'm going to end up producing, in this case, a ketone, where I end up with all my carbon atoms there. I'm going to end up with a double bond here, and then one lot of water as well. And there's that last equation done, the oxidizing agent, and of course the water is going to balance too. So moving on to our next task then, I want you to try the following. Pause the video, resume once you're ready to go over the answers. So starting off with the first one then, we've got the oxidation of ethanol using reflux apparatus. Here we've actually got an aldehyde. It's not going to be a primary, secondary or a tertiary alcohol. We don't actually end up with, of course, water being produced in this case. We do form a carboxylic acid. So I've got ethanol over here. That's going to react with, of course, one lot of oxidizing agent. And we end up producing our carboxylic acid, which is just going to be ethanoic acid in this case. And so there's that one done. Remember, there's no water produced in the second step of oxidation to form a carboxylic acid. Looking at the next one, we've got the partial oxidation of the following compound with the distillation apparatus over here. Now here we've got multiple alcohols. We need to classify each one of them. So of course we look at the first one. You can see, of course, I've got one alkyl group attached there, so that's going to be primary. Look at the second one, you've got two alkyl groups attached there, so it's going to be secondary. Now if you look at this again, remember it's partial oxidation, it's distillation apparatus. We're not producing carboxylic acids, we can only produce aldehydes and ketones. So we end up, of course, in this case, using some oxidizing agent. We'll balance it at the end. We end up producing a ketone at this position over here, and then over here we actually produce an aldehyde as well. So in that case, right, we've got to balance it. Don't forget the water as well. I need two lots of oxidizing agent, one to oxidize the primary, one to oxidize the secondary. I end up producing, of course, a ketone and an aldehyde. I need two lots of water being produced over here as well. And there's that one done. Normally in a question like this, if you balance it, you get an extra mark as well. Now look at the next one, the complete oxidation. So again, we're using reflux over here. We're looking at the complete oxidation of this compound. You can see over here I've got an aldehyde, so it's not going to be an alcohol anymore, it's going to be an aldehyde. We've got over here a secondary alcohol because there's two alkyl groups, and then of course we've got here a primary alcohol as well. We've got, of course, one alkyl group. Now if we were to look at it, we're completely oxidizing this to the max. So in that case we end up with oxidizing agent. We end up producing, of course, we've got 1, 2, 3, 4 carbon atoms. So I'm going to draw it out like this as well. It's quite a hard one to draw, this one. I'm going to end up with, of course, my carboxylic acid being produced over here. So I've used two lots of oxidizing agent here. The next one is of course the ketone is produced over here, so I've used one there. And then of course our aldehyde to a carboxylic acid, that's going to be one lot of oxidizing agent as well. So altogether I've actually used 4 lots of oxidizing agents. Count this carefully. Now in terms of water, I'm going to do this in a different color. I'm going to produce 1 lot of water from this primary alcohol forming an aldehyde, and then aldehyde to carboxylic acid, there's no more. Secondary alcohol produces a ketone, that's another lot of water. Aldehyde, of course, that produces a carboxylic acid, that's going to be, of course, no lots of water. So in total I end up with 2 lots of water being produced. And of course you get 1 mark for the actual equation and the structures of the organic compounds, and then 1 mark for, of course, the waters and the number of lots of oxidizing agents as well.